Let's get started. So today we're very happy to have with us Shayan Oveis Gharan, and he's a PhD student at Stanford under the direction of Amin Sabari. He works on approximation algorithms and has some really amazing results, including a breakthrough result for approximating asymmetric TSP problem. And he's going to be here for today and also all day tomorrow, so if you'd like to meet with Shayan, you can send Jason an email. So today he'll talk to us about rounding by sampling approach to the TSP problem.
Thanks for inviting me, and thanks for the nice introduction. So yeah, I would talk about the rounding by sampling method. Suppose we have a discrete optimization problem, and we want to find, let's say, nearly optimal solution. Usually, it's not easy to do this directly. So instead, we use this path. So we start by modeling the problem as an integer program. But integer programming cannot be solved efficiently. So what we do is that we relax the integrality constraint, and we look at the continuous relaxation, or like linear program or semi-definite program. Then we can use the LP solvers to find the optimum solution of linear program. So we get the optimal fractional solution. Now, there is this last step that we need to find an integer, a near optimal integer solution based on the fractional solution. So this is the rounding step. Usually all of the three first steps can be done automatically. There's a machinery to do that. And the last step is the heart of the arguments. So I would talk about rounding methods. So there are different rounding methods, like lots of different, for different problems. Like here are some, like 3 of them I selected. So perhaps the first one that comes in mind is the independent rounding method. This is the method of Ragavan and Thompson. And then here you kind of round each variable, each fractional variable independently to 0 and 1. Then there is another version which is iterated rounding method. Here we utilized extreme point solutions of the linear program. This method has been applied to like Steiner network design problems, bounded degree spanning trees, and so on. But today I would talk about the rounding by sampling method. So this method has been used more recently to a variety of problems, including traveling salesman problems, maximum fair allocation, matching problems, online matching problems. But today I will mostly talk about the application to traveling salesman problem. So here's the outline. First, I would define the problem. Then I will define the rounding by sampling method, and I show you how we can design an algorithm based on it for traveling salesman problem. And finally, I will give like approximation algorithms for the asymmetric and symmetric version of TSP. So let me define the problem. So in traveling salesman problem, we are given a set V of vertices and a non-negative cost function C for each pair of vertices. And the task is to find the shortest closed tour that visits every vertex of the graph at least once. We want to find a tour that exists. And without loss of generality, we may assume that the cost function satisfies the triangle inequality because we can shortcut the vertices that we see. So the special case of this problem is the symmetric TSP, where we assume that the costs are symmetric. The cost of going from U to V is equal to the cost of going from V to U. But asymmetry also may happen. For example, if we have one-way street symmetry. Okay, so by STSP, I mean this version. By ATSP, I mean the asymmetric version. So let me show you a cool application. This is a application. This is the application I recently read about called traveling politician problem. So it turns out that almost all of the candidates in the Republican campaign visited all of the 99 counties of the Iowa state during the pre-election, and so usually because these guys have limited time, their time is valuable. It's crucial that they use the shortest tour to visit all these counties. So this is the tour that William Cook with co-authors computed, and we show that this is the optimum one. So it's good that they use this tool.
That's the way. That's optional.
Okay. Okay, so since I promised to round continuous relaxation of the problem, let me define the relaxation that I'm going to use. So this is also known as the health card relaxation, and here is the linear program. So remember, C was the cost function on the edges. Let's say x of a is the fractional value that we assign to the edges. For a set S of vertices, delta plus of S is the set of edges that leaves S, and delta minus set of edges that comes into S. So what this constraint says is that at least two edges should leave S for any set S of vertices. Any tool would satisfy. Sorry, this should be one. Sorry, this should be one. Yeah. Sorry. So this says for any set S of vertices, at least one edge leaves it. Okay, so this should be one. And this one says for any vertex, we should have at least one edge coming into it and at least one edge going out of it. Okay. So if we force this value x's to be integral, then we get the optimal solution would be an integer two. Because this is the connectivity constraint is connected, and every vertex has.
I'm getting a bit confused on this notation. So what's x?
X is for an integer constraint. You assume it's a 0-1 variable. But if you relax it, you.
But what does this relate to the TSP?
So it says whether or not you're gonna choose this edge.
So
in the tool.
So A is an edge.
A is an edge.
A directed edge.
A directed edge.
And x of a says whether I can choose it for.
Right. So you want.
And what is x of delta plus of s?
It says you have at least one edge going outside of each set. It should be one.
So delta plus is a set of edges going out of set S. And delta minus is a set of edges coming into
a set. And so that condition is really saying the sum of the xi's in that set is at least 2, no, why 2 and not 1?
Yeah, that's what
no, it should be 1, not 2.
Oh, it's a typo on that.
Yeah, it's a typo.
That's what you were saying. Okay. Okay.
You have at least one is going outside of each set, and you have, for each vertex, you have one incoming and then one outgoing.
And that second condition is not really.
Yeah, this is not really.
I mean,
so what you need is that these two should be equal.
Okay.
But even this would work because the optimum solution satisfies this. So it's gonna look. And if you wanna look at the undirected version, you can just drop the directions. So for each cut, then you would have two edges, from S to S complement, because originally in directed version we have one in this direction and one in the other. So in the undirected we have two in between, and for each vertex in the undirected version we have two edges adjacent to it. So okay, so we cannot solve the integer program. We relax it and we allow this x values to be fractional. And okay, so this optimal solution, this linear program can be computed optimally using, like, for example, the ellipsoid method. You should not be worried about it. So also the integrality gap is defined as the worst case ratio of this of the optimum integer solution and the optimal solution of this thing. It is clear? So we are interested in designing approximation algorithms. So by an alpha factor approximation, I mean an algorithm is an alpha factor approximation if it always produces a solution which is within factor alpha of the optimum. Okay? Now, because usually it's hard to compute the optimum, the actual optimum, we'll look at the a lower bound on the optimum solution. So typically, people use linear programming, the solution of the linear program as a lower bound on the optimum solution. So if I prove that algorithm is less than alpha times LP, it would be a alpha factor approximation. Okay. So let me now say what we knew before and what we can show. So classically, this is what we know about symmetric and asymmetric version. There is a 3/2 approximation by Christofilis, and probably many of you have heard. This is for symmetric TSV, and it has been widely open to improve this 3/2 approximation. For asymmetric version, there has been an order of log n approximation by Fries and co-authors. So here's what we do. What we did, we give a log n over log n approximation for asymmetric version. This is a joint work with Asadpour, Gomez, Madgi, Sabri. And we also give a better than 3/2 approximation for symmetric version, but this is not for all metrics. This is for graphic metrics. So these are the shortest path metrics on unweighted graphs. So you can think about it like we have an unweighted graph, and we want to find a tool that visits each vertex at least once. For these kinds of graphs, we can get better than 3/2.
To get better, like were other results known for better than 3/2 for the symmetric case for certain graph structures?
Not like for some very limited, like if the graph is unweighted and it is 3 regular and 3 connected, we knew that we can do better than 3/2 before.
When you say 3/2 minus epsilon, there's some particular epsilon you have in mind?
Yeah, so this epsilon is
You
a
just don't want
constant.
to tell us what it is.
Yeah, it's very small. But but this, yeah. It's less than 10 to the minus 10.
So maybe we shouldn't just all jump to switch algorithms.
So one nice thing is that, I mean, as I will show, the algorithm is, the algorithm would be similar to the Christofilis, but we can surely prove that it's always as better as Christofilis. So you would not lose anything by using this algorithm. But this is the performance guarantee that we can prove. I mean, I suppose it could be better really in practice if you are interested. But yeah, we cannot right now prove better than that down. We also think that this algorithm actually works for the weighted version, not for this particular version. But we cannot prove it.
Is it well known that this 3/2 approximation is tied down?
No.
No, I mean, so for that particular algorithm.
Yeah, for this algorithm it is tight, yeah.
So your analysis is not tight for your algorithm.
No. Okay, so next I will describe a rounding by sampling algorithm for this problem. And interestingly, the algorithm would be almost the same for both of the asymmetric and symmetric versions. So before describing the rounding by sampling method, let me give a simple observation. It turns out that there is a fractional spanning tree hidden in the solution of LP. Okay. So what do I mean? Let's say this is the LP relaxation, and let's say X is an optimum solution. X will be optimum solution throughout the talk. Now let me define this vector Z So I first drop the direction for like I add up xuv plus xvu for any u and v, and then I multiply it by n minus 1 over n factor. Now my claim is that this vector z is in the spanning tree polytope, meaning that it can be written as a convex combination of spanning trees. So why is that true? First of all, the summation of x values of the edges here is n, because each vertex has out degree 1. So if you multiply by n minus 1 over n, you would get fractionally n minus 1 edges. And every tree has n minus 1 edges. And there is one other technical condition you need to show, which is that every subset of vertices, the summation of fraction of edges inside it is at most the number of vertices in that subset minus 1. But should not be scared about that. And that's going to be satisfied. So this vector z is in the spanning tree. So essentially what we want to do is that we have a fractional spanning tree. We want to round it to a 2. Okay. So let's start by a simple rounding. Let's try the independent rounding of Raghav and Thompson. So what do they say? They say let's round each edge independently. So for each edge, I'm going to toss a coin. It's probability z of e. I'm going to set it to be 1. Probability 1 minus z of e. I'm going to set it to be 0. Very simple. So this way, the probability of choosing a subset f would be z of product of z of e for edges inside f, and 1 minus z of e for edges in out. Now, okay, here are the caveats. So this method has a nice property that the marginal value of the edges are preserved, meaning that for any edge, it would be the probability that we included is exactly equal to its LP value. So somehow in expectation, we have the LP solution. But a bad thing is that we lose the underlying combinatorial structure. So we can show that at high probability that the rounded integer solution is not connected. We lose connectivity.
And it also might have cycles and stuff. It's not necessarily a tree.
Yeah, it's not necessarily a tree. And we can show this leads to not better than order of log in approximation for ATs. So what I'm going to do instead? So let's say I have this fractional point z in the spanning tree polytope. Or this could be any polytope in general, an integer polytope. Now, I'm going to write z as a convex combination of integer points, of the extreme points of the LP. And because my LP is integer, the extreme points are going to be a spanning tree. So I'm going to write z as a convex combination of spanning trees. Say P1, T1, plus P2, T2, and so on. And then I'm going to define this distribution by choosing Ti as probability Pi. Now, it turns out that the probability of choosing each edge is still equal to its value in z of e. So we can say for any linear function for any cost function or any linear function in general, the expected cost of the sampled tree would be equal to cost of z. In particular, if I sample a tree like this, the expected cost of a tree would be equal to the cost of the LP. Okay. So note that this method is very general. You can apply it to any integer polytope here, and you can choose any convex combination you like. Okay. So let me use this degree of freedom to choose a particular convex combination. So I will choose a particular convex combination to get more properties. So let me so here's the idea. The idea is to avoid imposing any additional artificial structure. So we say let's keep the combinatorial structure intact while preserving the marginals. So we say I want to look at a distribution that preserves the marginal value of the edges while being as random as possible. Okay. So what does it mean being as random as possible? It means look at the maximum entropy distribution. This distribution has the least least amount of information. So let's say for every possible tree in my graph, I assign a probability PT. There could be exponentially many of them. Then the entropy of this distribution is just going to be summation of minus PT log of PT. Now I would have this. This is just a marginal probability. I would say for any edge E, the summation of the trees that has this edge is exactly equal to Z of them. Okay, and these are probabilities; they're not negative. So, what is the benefit? If you look at this convex program and you write the KKT conditions, you can show that the optimum solution, the probability of each tree is a product distribution. So there are weights lambdas you can assign to the edges, such that the probability of each tree is equal to the product of the lambdas of its edges. Okay, I will show next example next. So for example, let's say if these lambdas were all equal to 1, then you would get a uniform distribution of spanning trees. Okay. And it turns out that this weight lambdas can be computed in polynomial time because we can provide we can use ellipsoid method to compute the optimum solution of this convex program. So let me show you an example. Suppose this is our graph. Okay, so it has 3 edges. These are the probabilities of the edges. Note this solution is in the fractionals, is in the spanning tree polytope. Now, turns out that if I choose lambdas like this, let's say this edge is 1 over square root 8, this is 2 over square root 8, 2 over square root 8. Then I would have 3 spanning trees. Right? I remove each of the edges. Now, what is the probability of this tree? It's going to be 1 over square root 8 times 2 over square root 8. This is going to be 1/4. This one is going to be 2 over square root 8. It's going to be 1/2. 2 over 8. Sorry, 4 over 8. 1/2. And this one is going to be, again, 2 over 8. It's going to be 1/4. So we get 3 trees. And now, like the probability of this edge, for example, is contained in these 2 trees. Each of them has probability 1/4, so the probability of this edge would be 1/2. Right? So we get a distribution. We assign lambda values such that the corresponding distribution has the same marginal probabilities.
Should
One of
the
the
bottom
edges
edge
should be 0.75.
0.75?
The 0.75 on the second bottom edge.
Say it again?
The bottom edge and the
Bottom
top
edge is
triangle
at
should be
0.75.
0.75, not
Oh.
0.5.
Yeah. Yeah, you're right. Sorry, this just should be 0.7. Yeah, that's one. Yeah. Okay. That is clear?
So, like, can you go back a slide? So you're saying for the PT that solves this maximization problem, there exists lambdas for the edges such that this happens.
Right.
And what's lambda uniforming? You're just selecting the edges according to.
I will call this lambda uniform distribution because it is in some sense similar to uniform distribution. If lambdas were all equal, then we would get uniform. So if lambdas are not, it's a variant of uniform distributions on spanning trees, and it actually preserves a lot of properties, like all properties that they do preserve. So yeah, we call it lambda uniform distributions.
What is Z sub E?
Z sub E was the marginal value of the edges. So this was the vector Z we get it by n minus 1 over n times x.
Z sub E is in the spanning tree.
The spanning tree polytope, yeah. And another thing is that you can look at this as the uniform spanning trees. by, like, if you multiply every lambdas by some very large constant, so that they become all integral, then you will still have the same distribution. It's going to be proportional to this value. But then you can, for each edge, you can put lambda e copies of that. So you would get a uniform distribution on that graph. So this is why kind of look at that. And that is actually why these distributions satisfy the properties of uniform distribution.
And you're claiming you can find these lambdas through the K.
So we can find them by the ellipse sort. KKT would just prove the existence.
So it's only approximation. And it would never give you the exact solution.
Right. Yeah. So yeah, we give an approximation. Yeah, but you can get as much as, it's like the LP. You cannot actually find out, but you can get as much as you like close to that.
No, I didn't get the answer to the first question. Does ellipsoid compute both P and lambda or just P?
No, the ellipse, you cannot compute P because P has exponential support.
Right.
So you just compute lambdas, but the P and the P's are just in here. Okay, so what we did prove, we kind of say, we said for any solution of the LP relaxation of ATSP or TSP, we can find a lambda uniform distribution on spanning trees that has, almost like Z really close to X of E as the marginal of the edges. The probability of choosing each edge is exactly equal to X of E.
I got confused. You switched X to Z.
Yeah, this is why it's almost, if you put ZE, it would be equals, but XE and ZE are just n minus 1 over X, so they are. Okay, so next I'm going to show you how we can use this to design a rounding algorithm for TSP. Okay. This would be our tool. Okay, so this is the algorithm for both TSP and ATSP. So up to this step is easy. So first we compute X, the optimum solution of LP, and Z, of course. Then we compute the lambda uniform distribution, compute the lambda values that have Z's as the marginal of the edges. Then we sample a tree T from this distribution.
How do you do that?
So you can, there is a vast literature for sampling from uniform spanning trees, and that can be done for even lambda uniform. I mean, you can make your distribution uniform with just putting many edges, so you just sample it. You can use Markov chain, random walks, or like there are many ways to do it. Okay, so we sample this tree T. Now what we do in the last step, we make T Eulerian by adding the minimum cost set of edges to make it Eulerian. So what does this mean? In case of ATSP, we add the minimum cost set of edges to make the in degree of each vertex equal to its out degree. And in case of TSP, we add the minimum cost set of edges to make the degree of each vertex even. So then once we have a subgraph, like every vertex has even degree and it is connected, it would give us a 2. You can just shortcut the vertices that you see multiple times and then you get actually a cycle.
Is that the same as the Christophilus?
Right, exactly. So the Christophilus algorithm actually does this step, but instead of the first tree, it just samples the arbitrary minimum spanning tree. So what we say is that, okay, let's say a random tree instead of a minimum spanning tree. So minimum spanning tree is bounded by LP, random tree is also bounded by LP, so you would not lose anything by using the random tree. But hopefully this last step wouldn't cost you that much if you use a random tree. Is this any other question? This is a good place.
So it doesn't even solve the LP, just pick some tree at random.
It solves the LP.
But then picks each edge independently. Or what?
No, it solves that it computes the lambda values to have the LP value or their normalization as the marginal probability of the edges. So it looks at the LP, it says, okay, I have these values on the edges of the LP. Which distribution, which uniform distribution on trees would give me these probabilities for the edges? Like this, let's say, let's say this, for example, the solution of LP. I want to find the distribution, I want to find weights on the edges lambda such that gives me this distribution.
I was talking about the other solution of the other.
Oh, the Christophilus. Yeah, the Christophilus, yeah, it even doesn't look at the LP. You're right.
So, your distribution we have here also includes three spans that are not minimum, right? Or it's this uniform distribution, like it includes, we have a uniform distribution over spans. So does it also include spans that are not minimal? So
yeah, of course. Yeah.
So
the expectation that this kind of thing would be the LP, but it could be some of them could have larger costs than the LP. But expectation you'll find.
Well, if it's about, if the expectation has to be the minimum, then everything has to be the minimum, right?
No, it could be some of if they expect so. So in general, it could be that minimum spanning tree is smaller than the solution of LP. Then some of them could be smaller than solution of LP. So the rest of the talk, I will show you how we can analyze. Sorry, I should mention one more thing. So this last step can be done in polynomial time, optimal. I will talk about it later. But so the rest of the talk, we want to analyze this algorithm. So let's start slowly. Okay. So remember this J. By J, I mean the Eulerian augmentation. I will use J for this. Okay. So I can write the cost of our algorithm as the summation of the cost of the sample tree plus the cost of the Eulerian augmentation by the negative expectation. Now, this one is easy to analyze. By rounding by sampling method, I know the expected cost of tree is at most the optimum of LP. This is fine. So all I need to do is to analyze this part. Now, here is where we're going to use the randomness of T. So for ATSP, I'm going to show that the cost of the Eulerian augmentation is bounded by log n over log n of the optimum with high probability. And for TSP, symmetric TSP, I'm going to show that this is bounded by 1/2 minus epsilon of the optimum for some constant. Okay, so we should agree that these two just finishes the proof. So let's start with ATSP. So I would give a log n over log n approximation. So let me say how we're going to use the randomness of tree. This is the crucial part that you could not have do that in the Christophilus algorithm. So we're going to use the nice properties of uniform distribution and spanning trees, which is this negative correlation. So knowing that an edge E is in the sample tree would decrease the probabilities of the rest of the edges. So formally, for any set f of edges, I can say the probability that all these edges are in my sample tree is less than the product of the marginal values of the edges. So note that if I was rounding independently, I had equality here. The probability of having these edges would just be equal to the product of the marginal value. Now, negative correlation kind of gives me something better. It's so what's the implication is that we know that with independence we could have proved Chernoff types of bound. So negative correlation is even better. So we're even closer to the expected value. So we can kind of prove every chain of types of concentration values. So in particular, I can say for any set F of edges, the probability that the intersection of my tree with F is more than 1 plus delta of the size of the intersection of my tree with F is more than 1 plus delta of the expectation is at most this much. Very typical. Now, let's plot delta equals log n over log n. I can say with high probability, the intersection of my tree with F is at most log n over log n of the expected value. Now let's apply this to the cuts of the graph and take a union bound. So I can say with high probability for all cuts, the intersection of my tree with the edges of a cut is within log n over log n of its expected value. Note that the expected value of a cut is the summation of the z of edges in that cut, because the probability of each edge being in tree was 0. So let's see what this means. This means that my tree is within log n over log n of the optimum 2. Right? Across each cut, it has at most log n over log n more edges than the solution of LP.
Why does that imply what we're doing?
Because like with high probability for all cuts, this is less than log n over log n of this value. And this is just the size of LP in that cut. So the number of edges of my tree in any cut is at most log n over log n of the size of the cut in the optimum. So in some cuts I could be equal, but in the worst case, or all cuts, I'm at most log n over log n.
How did you get the z on the right-hand side of the inequality?
This one?
No. Inside.
So z is the expected value of this guy.
Why? Oh.
Because this is just linearity of
Sampling according to-
expectation. Yeah, this is just rounding by sampling. Okay, so we're almost done for ATSP. So let's say this is a sample tree. We want to extend it to a 2. So first let's plug in back the direction of the edges. What we want to do, we want to add, let's say these gray edges are the edges of a graph. You want to add the minimum cost set of edges to make the in degree of each vertex equal to its output. So this is just a min cost flow problem. And it can be computed in polynomial time. We want to basically route one unit of flow from the head of each edge to its tail. Okay? This can be computed in polynomial time. So we just need to bound the cost of it. So by what I just said, we know that for each cut, the number of green edges from this side, from left to right, is at most log n over log n of the number of gray edges from right to left. Because we are at most log n over log n more than the other. So by Hoffman's circulation theorem, all we need to do is to just boost the LP by log n over log n. This way we can have as much edges from right to left as we have from left to right. And this is sufficient. This is necessary and sufficient. So this simply says the cost of the Eulerian augmentation is the most log n over log n of the cost. Right, so the point is just need to equalize the two sides, the two directions. It may have much more edges, so we just boost the LP to make the two equal.
The Hoffman theorem says that if for any cut, the set of edges that pass that cut is at least 1, then is it?
It says if this gray edge is more than, if the edges that gray edges that from that enter the cut is more than the green edges that you force is sufficient to find a flow. So actually once you want to apply this, you're going to run a lower bound flow. You want to put a lower bound of 1 on the green edges, but then this circulation says we can just add gray edges to satisfy the lower bound. And this is the solution.
Can you go back on your slide so how you put this balance? So you channel about to put the LD cut out.
In every cut, the tree has at most log n over log n more edges. I mean, log n over log n times the size of the cut. So if you multiply the cut, you will get as much edges as the tree has, fractionally, and that is sufficient.
You channel about and union about.
Yeah.
It's not trivial.
Okay.
I don't see how that comes from that one.
So there is a caveat here. You need to use the fact that the number of cuts of size alpha times the minimum cut is at most n to the minus alpha. Like the number of minimum cuts of a graph is 1 over n, or 1 over n squared. Number of cuts of size 2 times minimum cuts. We can talk about it offline, but this is all in this. Okay, so good. Let me conclude.
When you run this flow problem on this graph, you end up, the green edges are integral, right? And the gray edges may be fractional.
Right.
And so when you say you're boosting the flow solution,
The LP solution.
Now I'm confused because we were solving a flow problem here. So I don't know what you mean by LP solution.
Right, so what we're going to actually do is that we're going to put a lower bound of 1 on the green edges and an upper bound of LP times log n over log n on the gray edges. What this theorem says is that if the upper bound on the edges coming into the cut is more than the lower bound of the edges going outside of the cut, this is sufficient to get a feasible flow.
I'm confused as to why you have an LP again, because in your first step of your algorithm, you solved an LP, right? And that gave you these marginals. And then you randomized over trees with these marginal probabilities to get these green edges, which are now a tree. Right? Now, what LP are you talking about?
The original LP, the LP of ATSP.
The original LP. So now you're going back to the original LP to do something.
Right. So the thing is, I want to make this tree Eulerian. Now, it could be that some of the cuts are very bad. Like almost all edges are going. Like if the tree want to be Eulerian, I need to have the same number of edges from left to right and from right to left. If I have this over all cuts, I'm done. Now it could be that some of the cuts are very bad. So I have a lot of edges going this direction than the other. So I need to get the aid of LP, use the LP to balance it. If I have to
use a tree, right? Why do you go back to the origin?
Because
balance with this tree.
No, so I would add the edges from the LP because with this tree, the tree is not balanced. So I would add edges from the LP to make it balanced.
But not from the original LP because you already picked some. You select some set of edges. Now you select.
No, but he has the inequality in the probability of the Chernoff bound that the weight of the green edges, is compared to the z from the LP, that z variable from the LP. So if he boosts that z variable by log n over log n, then he knows that by the circulation theorem that he can find the edges going back that are going to complete the cut.
So the nice property is that I can kind of say the tree looks like the LP. So almost it has some imbalancedness. I can use the LP to make it correct.
And you're going to use the z variables, boosted z variables as capacities in the flow process.
Exactly.
Got it.
Now, going back to the beginning of the argument, Where are you using the fact that those lambdas are the multipliers?
Right, so we use it here to prove the negative correlation.
And so if they're
So
epsilon...
this property is true for uniform or lambda uniform distribution in spanning trees, but not any distribution in spanning trees. You can have distributions that doesn't like this. If you include some edge, it would increase the probability of others. So if you don't have negative correlation, you don't have Chernoff bounds. You cannot say in every cut I am almost equal to the LP. It could be that in some cuts you have much more edges than the LP has.
And so going back to his comment, if they're epsilon multipliers, if they're not the right multipliers, if they're off.
Right. So no. What do you mean they're off? So we might.
We didn't solve the problem exactly.
Right. So we don't compute the lambdas exactly. We compute them within epsilon of what they should be.
Yeah.
So so still it's gonna be a uniform distribution because whatever lambda values you plug in here, you still get a uniform distribution.
Yeah.
Now the thing is, you may not be able to say I'm gonna satisfy the marginal value of each edge exactly, but then you're gonna satisfy it within some epsilon factor. So then here, instead of saying you're going to be at most log n over log n of the size of LP in that car, you're going to be log n over log n of 1 plus epsilon on the size of LP.
Okay.
So you would not do that.
All right.
Good. So in the summary, we give for HSP, we give log n over log n approximation. And here's a nice open problem. You can write the solution of LP as a convex combination of cycle covers instead of spanning trees. And then you can apply the rounding by sampling method to cycle cover polytope. And so this is currently what we're working on. And it may be possible to get better than log n over log n in this way.
But when you do the cycle cover, then you lose all the connectivity property.
So then you can use multiple cycle covers. You can sample multiple cycle covers. Because each cycle cover is LP, so you can sample log n over log n. And you can also think about special cases. For example, here we show there's a constant factor for planar bounding genus. So let me go quickly to TSP. How much time do we have? 5 minutes?
Like 2 minutes.
2 minutes? So let me say it very fast. So for TSP, we want to bound the cost of the order augmentation. We want to say it's less than 1/2 of the optimal. So what is the difference here? Here we want to add some edges to make the degree of each vertex even. And this is a minimum cost matching problem. Okay, so this can be done optimally. But so we need to bound the cost of order augmentation again. So all we need to say is that we want to add some edges to make the to have even number of edges across each cut of the graph. Let's say if this cut has 3 edges, odd number of edges, we want to add 1 more edge. So here we can use Edmond's theorem. And what this says is that if you want to you can find an Eulerian augmentation if you have a solution such that you have fractionally 1 edge across each cut that has odd number of edges in the tree. Okay, so because you need to add 1 edge to each odd cut. So if you have at least 1 edge in each odd cut, it's sufficient. Now, what can we do it? How can we do it? The simple way is to scale every LP value by 1/2. This, because in LP we had fractionally 2 edge in each cut. In this way we had 1 edge at least in every cut, not just the odd cuts. So we can get a feasible solution, and this actually shows that the cost of the Eulerian augmentation is at most 1/2 of LP, no matter what tree we use. Now, you might want to say, let's scale every edge by 1/2 minus epsilon instead of 1/2. But this might go wrong because you can have some odd cuts with odd number of edges of the tree, such that their value in LP solution is very close to 2. Now, if you scale down every edge by 1/2 minus epsilon, these cuts become less than 1. So you would not have a feasible ordinary argumentation. So for this part, what we do is that we're not going to scale down every edge by 1/2 minus epsilon. We're going to scale down some of the edges.
So without this minus epsilon, you're getting the 3/2.
Yeah, this simply gives a 3/2 approximation. And if you can do it, you get better than 3/2. And this is even true for the weighted version. So what we're going to do is that we're going to say for some of the edges, we can decrease their value to 1/2 minus epsilon and still preserve this property that for all odd cuts, we have at least 1. So to do this, we kind of have to use 2 flavors of arguments. One of them is the properties of random spanning trees, and the other is the structure of near minimum cuts of a graph, cuts that have values very close to 2. So we kind of use this to talk about properties of near minimum cuts that become odd or even. So I think I would not have enough time to continue on this. So let me how is this? Okay. So at the end of the day, what we do is that we say if an edge is not in any odd near minimum cut, we scale it down by 1/2 minus epsilon. Otherwise, we scale it down by 1/2, and this would work. You can ask me after the talk why it would. And so this part we give 3/2 minus epsilon for this graph matrix. Now it's a fascinating open problem to see if this algorithm can work for arbitrary metrics. And there's also an interesting problem to see if we can get better than this 3/2 minus epsilon for graph metrics. And people already did a lot of nice work after our paper. So they ended up with 1.4. And still, this goes on. So, okay, let me conclude. So we use the rounding by sampling method. We apply it to ATSV and TSV. Now, during the work, we use this maximum entropy distribution, and we show that the optimum solution of this distribution is a lambda uniform measure on spanning trees. This enables us to talk about negative correlation of edges and Chernoff types of bounds. Chakuri, Wondrak, and Zinklerson show that this rounding by sampling method can also be applied to any arbitrary matroid polytope, matroid or generalizations of spanning trees, such that still negative correlation and Chernoff bounds are preserved, but they use different kinds of distribution, not the maximum entropy distribution. With maximum entropy, there is a caveat of computing it for arbitrary matrices. It's not easy. So this method, the rounding by sampling, has also recently been applied to a variety of problems. We applied it to online stochastic matching. It has been applied to the TSV path problem, and also we apply it to the minimum KR connected subgraph or strongly connected subgraph problem. You can ask me about these applications after the talk. But still, I believe it can have a lot other applications in other domains. Yeah, that's it.
Do you have any lower bounds on your algorithm for symmetric or asymmetric?
For asymmetric, we know it doesn't get better than log n over log n. But for symmetric, we don't. Right? Even for the weighted version, it could be.
So do you have any intuition about what problems such a technique is useful for?
So generally, I mean, I believe, like, I mean, usually if you if you write an LP relaxation for your problem, and if you can look at the LP relaxation, so the solution of LP relaxation inside some integer polytope, then these kinds of methods can be useful.
Because you're
You're gonna get
indices of this polytope.
yeah, because you can at least say every linear constraints on the edges or elements are going to be preserved in expectation. These guys can also talk about the submodular functions on the elements. But even if your integer polytope has more structure, it's a metro, you can say much more. So for example, for a TSP, I mean, it's also crucial that sometimes it might not be trivial at the beginning, because for TSP, it may not look at being a spanning tree polytope. You need to be careful about it. So in general, I believe, like, because if you write an LP relaxation for some intractable problem, it's not an integer polytope. So you may not directly be able to apply it, but still you may be able to change it a little bit and make it as a solution of integer polytope. But even like for this, in this paper, we applied it to some online domain problems too. So, I mean, this problem was easy in offline domain, but in online domain, you may also be able to use it. So, yeah, I would say whenever you can come up with an integer polytope, think about it.
Okay, thank you.